Right, so we're going to go through this question here where we have to draw the mechanism for this reaction, and then we have to decide out of product A and product B which one is the major product, so which one is going to be formed in the higher percentage. So let's firstly start off with the mechanism. So we're reacting it with hydrogen chloride, which is a hydrogen halide. So we draw the alkene out the way that it is, showing the double bond. We then need to draw our hydrogen chloride molecule. And whenever we're doing the mechanism, we have to show the relevant dipoles. So across our hydrogen chloride molecule, we do have a dipole. Electrons lie closer towards the electronegative element, which is chlorine. So the dipole across this bond is delta positive on the hydrogen and delta negative on the chlorine. This is now going to act as an electrophile. So an electrophile is an electron pair acceptor. Our hydrogen delta plus here will want to accept a pair of electrons because it's electron deficient. And that's why this mechanism is called electrophilic addition. Electrophilic because we've got this electrophile here, and it's an addition reaction because we're going to end up with one product. Okay, but there are two possible products that can form, but just from one molecule of this alkene here and one molecule of hydrogen chloride, we can only form one product, and that's why this is called an addition reaction. There are just two possible products that could form. Right, so in terms of the mechanism here, we have to draw a curly arrow mechanism, and that's where we show the pair of electrons moving. Okay, so curly arrow is showing the movement of a pair of electrons. Our double bond here is electron rich because it has 4 electrons between these two atoms. Okay, you have 2 electrons in the sigma bond and you have 2 electrons in the pi bond. So that's why this is very electron rich here. We're going to have a pair of electrons from the pi bond going to form a bond with our hydrogen in the electrophile. And then the HCl bond must break, because when you form a bond with the hydrogen here, hydrogen can only have a maximum of 1 bond. And that means this bond here must break. It breaks via heterolytic fission, which means both the electrons here go to our chlorine. So there are 2 possible things that can happen here. Okay, so I'm going to draw both of them, and over here each route is going to lead to a different product. So one thing that can happen is, I'm just going to keep the C3H7 the way it is, like that. One thing that can happen is that our hydrogen bonds to that very first carbon. Okay, and that means our carbocation is on this carbon here. Or we can have it the other way around, where the hydrogen bonds to this carbon here, and we have our carbocation on this first carbon. Okay, so there's 2 possible things that can happen. Each of these leads to a different product. So alongside our carbocation, we've also formed a chloride ion. Okay, so that chloride ion has a lone pair on it, and the same thing has happened down here. So these are the 2 possible routes. And just to complete the mechanism, we have the lone pair on our chloride ion donating electrons to our carbocation and therefore forming a bond with it. And therefore this product here is our product A. This C3H7, just remember that's just a propyl chain, so that's literally just 3 carbons with 7 hydrogens, like so. And so this one here is product A, and the other possible product, so that's completing this mechanism down here. If we have again the lone pair on the chloride ion going to the carbocation, we then form this product here. So the chlorine is on our first carbon. And again, I'm going to draw that propyl chain in full. So that's our C3H7. Or you could have just left it as C3H7, there's nothing wrong with that. Okay, so this one here is our product B. Okay, so that's the mechanism to form both product A and product B. We now have to decide which one is the major product and which one is what we call the minor product. So what we look at, if you remember, is our carbocations. Okay, so we have to classify both of these carbocations here, and we have to say whether they're primary, secondary, or tertiary. Okay, so this one over here, if we look at the carbon at which the positive charge is on, this carbon here is bonded to two other carbons. Okay, there's a carbon on this side and there's a carbon on this side. So that makes this a secondary carbocation. Okay, this one down here, so that's the positive charge there on this carbon. This carbon here, as we can see, is only bonded to one other carbon. Okay, so that makes this a primary carbocation. So the thing to remember here is which one is more stable. Okay, we don't have it here, but a tertiary carbocation, so that's a carbocation that's on a carbon that is bonded to three other carbons. Okay, so this here is a tertiary carbocation. This is more stable than a secondary carbocation. So as we just said, a secondary carbocation is where we have a carbon, so the positive charge on that carbon. This carbon is bonded to only two other carbons and one hydrogen. Okay, and this is more stable than a primary carbocation. So a primary carbocation is where the carbon is only bonded to one carbon and two hydrogens. Okay, so in terms of stability, primary carbocation is the least stable and tertiary is the most stable. Out of these two, so we have a primary and a secondary carbocation. Our secondary carbocation, I'm just circling the whole thing, but it's technically just this part, this is more stable than our primary carbocation. Because it's more stable, this is more likely to form, and therefore product A is our major product. Okay, so the one that goes via the secondary carbocation here is the major product. Okay, you could have done this, so in terms of explaining this in an exam question, it is better to use the explanation of which carbocation. So in an exam question, you would say that product A goes via a secondary carbocation, product B goes via a primary carbocation. Secondary carbocations are more stable than a primary carbocation, and therefore product A is the major product, and product B is therefore the minor product. Okay, you could have also gone via or using the explanation of Markovnikovs rule, but in an exam they don't always give marks for that. So you could use the Markovnikovs rule just for you to remember it, but as your explanation it's better to use the carbocation argument. According to Markovnikovs rule, the hydrogen in the hydrogen halide will bond to the carbon with the most hydrogens on it. So out of these two, so it's the carbons that are in the double bond. This carbon here is bonded to two hydrogens. This carbon here is directly bonded to one hydrogen. So this carbon here has the most hydrogens, so that means this hydrogen here will bond to this carbon. And as we can see, that is what happens in this route over here. The hydrogen has bonded to this carbon and the chlorine is bonded to this one. And that's why this is the major product. So Markovnikovs rule says the hydrogen in the hydrogen halide will bond to the carbon in the double bond with the most number of hydrogens, and that will be the major product.